Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Imagine you're a software engineer building a program to calculate the total lifetime revenue of a subscription service, or a statistician aggregating thousands of data points. If you had to write out every single addition step by hand, your code and your paper would be miles long. Mathematicians hate doing unnecessary grunt work, so they invented a compact shorthand to represent massive sums instantly. It's called the sigma notation. It's essentially a loop command for mathematics. Today, we're going to learn how to read this compact language, unpack its hidden instructions, and see how it completely streamlines our work with sequences and series. Now, before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. The sigma notation uses the capital Greek letter sigma, which is this letter right over here, and it stands for sum. Think of it as a machine with a starting instruction, an ending instruction, and a formula template. And how it works is we start with the sigma notation to indicate that this is a sum, so we're going to be adding everything together. Next, we're going to have an index variable, so this is the letter that you see under the sigma. And this can be k, I, j, any letter. The one that you see, which is what k is equal to, that is the lower limit of the summation, so that's where the counter starts. And this doesn't have to start at 1, it can start at any number. And the n is what's above the sigma, and that is the upper limit of the summation, meaning that's where the counter ends. And then finally, we have our function f of k, which is written to the right of the sigma, and that is the explicit formula for generating each term. So how it works is you start at the lower limit of your summation. So in this case, we start at 1. We're going to substitute 1 as our value for k into our function f. And then the counter increases by 1, so meaning k is now going to be 2. And we substitute 2 as the value for k into our function f. And we keep doing that until we hit our upper limit summation, which is n. And once we've substituted n into our function, that's where we stop. And the sigma notation here tells us to add up all of those terms. So let's take a look at how it works in action through our first example. So here our starting counter is k is equal to 3. So that means we start by substituting 3 into our function. So that means when k is equal to 3, our function here is 4k minus 5, which means this is going to be 4 times 3 minus 5, which is equal to 7. So this is our first term. And then we're going to iterate and move on to the next number. So that'll be k is equal to 4. Substituting it into the function is going to give us 4 times 4 minus 5, and that is equal to 11. And then again, we increase our counter by 1, so we get k is equal to 5. So then our term here is 4 times 5 minus 5, which is 15. And then we're going to keep doing that until our top number, which is k is equal to 12. And the term here is 4 times 12 minus 5, so this is equal to 43. So now notice that here the terms form an arithmetic sequence because we go 4 times 3 minus 5, 4 times 4 minus 5, 4 times 5 minus 5. So meaning from one term to the next, we are adding 4 every time. So this here is equal to 7 plus 11 plus 15 plus ... all the way until 43. And we can calculate that using our arithmetic series formula. We have our first term, u sub 1, is equal to 7. And then our last term, u sub n, is equal to 43. We know that the common difference here is 4. Now, as for the number of terms, our n here is going to be equal to the upper limit of our counter, which is 12, minus the lower limit of our counter, which is 3. But because this is inclusive, meaning it includes both 3 and 12, we must add 1 to account for that. So our n here is equal to 10. And now we can use the formula, so s sub 10 is equal to n divided by 2 times u sub 1 plus u sub n. And that's going to give us 250. So therefore, the sum is 250. And now let's take a look at our next example. So same thing, our starting counter this time is 1. So we start by substituting 1 into I, which means our first term is going to be 3 times 2 to the power of 1 minus 1. And then we're going to add the next term, which is when I is equal to 2. So that'll be 3 times 2 to the power of 2 minus 1. And then we're just going to do one more. So the next one is 3 times 2 to the power of 3 minus 1. And we're going to do this until the last term, which is when I is equal to 8. So this will be 3 times 2 to the power of 8 minus 1. Now let's just go ahead and evaluate each term. So the first one is 3 times 2 to the power of 0, which is 3. The next one is 3 times 2 to the power of 1, so that'll be 6. And then the next one is 3 times 2 to the power of 2, which is 12. And then the last one, that's going to be quite a big number because it'll be 3 times 2 to the power of 7, which is 384. So looking at this, we can see that we have a geometric series because each term is the previous term multiplied by 2. And that makes sense because the power of 2 increases by 1 every time. So which means to find the sum, we can use our geometric series formula. And we have our u sub 1 is equal to 3. The common ratio r is equal to 2. And n is the number of terms. And here, this is going to be equal to 8 minus 1 plus 1. So this is equal to 8, which means s sub 8 is going to be equal to the first term multiplied by r to the power of n minus 1 over r minus 1. And this evaluates to 765. So therefore, our answer here is 765. And now for our last example, we're going to take a look at a question that appeared on the IB exam back in 2024. So here we're given two sequences. The first is an arithmetic sequence, A, P, Q, where the terms are not equal to 0. And the second sequence is a geometric sequence, A, S, T, where again the terms are not equal to 0. So because this question is quite long, and I'm going to be scrolling down as I work, feel free to take a screenshot so that you can follow along. Now, the first part of the question, part A, is asking us to show that 2p minus q is equal to a. So because a, p, q is an arithmetic sequence, we know that they must share a common difference, which means if we take the second term and we subtract the first term from it, that's going to be equal to the common difference d. But this must also equal to the third term minus the second term, which means this is equal to q minus p. So then we have p minus a is equal to q minus p. And now if we move the p from the right side over to the left side, we get 2p minus a is equal to q. And now the last step is just moving the a and the q to the other side. So we end up with 2p minus q is equal to a. And thus we have shown this to be true. Now part B is similar, but this time we're working with the geometric sequence. And we're going to do it the same way. So the difference is that geometric sequence shares a common ratio and not a difference. So that means we're going to take the second term, dividing it by the first term, and that is going to be equal to the common ratio r. But that must also equal to the third term, which is t, divided by the second term, which is s. And now multiplying both sides by a and then multiplying both sides by s is going to give us s squared is equal to a times t, which is exactly what we're trying to show. And now the third part says that it is given that q is equal to t, which is equal to 1. And we want to show that p is greater than 1/2. So we're going to start by substituting the value for q and t into the equations that we got from parts A and B, which means we get 2p minus 1 is equal to a. And then substituting in the value for t into the second equation, we get s squared is equal to a times 1. And now we're going to take this equation for a and substitute it into the first equation. So that means we get 2p minus 1 is equal to s squared, which means 2p is equal to s squared plus 1. Dividing both sides by 2 is going to give us p is equal to s squared plus 1 over 2. So now let's examine this a little bit. We were given that s does not equal 0. So since s does not equal 0, that tells us s squared must be greater than 0, because it doesn't matter if it's negative or positive, once we square it, it's going to be a positive number. So if s squared is greater than 0, then that means s squared plus 1 must be greater than 1. And this means s squared plus 1 divided by 2 must be greater than 1 divided by 2. So therefore, since p is equal to s squared plus 1 over 2, we have shown that p must be greater than 1/2. Now part D says that given a is equal to 9, s is greater than 0, and q is equal to t is equal to 1, we're asked to write down the first 4 terms of the arithmetic sequence, as well as the first 4 terms of the geometric sequence. So let's start by writing out the arithmetic sequence. So we start with 2p minus q is equal to a. And then now we can substitute in the values for q and a. So we get 2p minus 1 is equal to 9, which means p is equal to 5. So therefore, our sequence would be starting with a, which is 9. The next one is 5. And then the next one is 1. And we can see that the common difference here is -4, which means the fourth term must be -3. So this is the arithmetic sequence. Now for the geometric sequence, we start with s squared is equal to a times t, which means we get s squared is equal to 9 times 1. But we're told that s is positive. So that means we only take the positive square root, so s is equal to 3. So that means our geometric sequence is going to be 9, 3, 1, and here we can see the common ratio is 1/3, which means the fourth term is 1 over 3. So this here is our geometric sequence. And now finally, part E says that the arithmetic and the geometric sequence are used to form a new arithmetic sequence. And we're given that the first term, u sub 1, is equal to 9 plus ln of 9. Our second term, u sub 2, is equal to 5 plus ln of 3. And the third term, u sub 3, is equal to 1 plus ln of 1. We're asked to find the common difference of this new sequence in terms of ln of 3. So we know to find the common difference, we just need to take a term and subtract the previous term from it. So therefore, that means we can calculate the common difference d by taking u sub 2 and subtract u sub 1 from it. So that means this is equal to 5 plus ln of 3 minus 9 plus ln of 9. And this is equal to 5 minus 9 plus ln of 3 minus ln of 9. But we can rewrite ln of 9 as ln of 3 squared. And now we can go ahead and use the power law to pull the 2 in front of the ln. So we get this is -4 plus ln of 3 minus 2 ln of 3. And then combining the like terms is going to give us this is -4 minus ln of 3. So this would be the common difference d for this new arithmetic sequence. And then finally, the last part of part E is asking us to show that the summation from I is equal to 1 all the way to 10 of u sub I is equal to -90 minus 25 ln of 3. So this is just saying that we want to go u1 plus u2 plus u3 all the way up until u sub 10, which means in other words, this is just equal to s sub 10. And we know exactly how to do that using the formula. So we have u sub 1 is equal to 9 plus ln of 9. We know that the common difference d, which is what we just found earlier, that's negative 4 minus ln of 3. And we know that n is equal to 10. So now all we need to do is put this into the formula. So we get s sub 10 is equal to n over 2, so that'll be 10 divided by 2, times 2 times u sub 1, so this is 2 times 9 plus ln of 9, plus n minus 1 times the common difference d, which is negative 4 minus ln of 3. And now this is just purely algebra. So we get this is equal to 5 times 18 plus 2 times ln of 3 squared plus 9 times negative 4 minus ln of 3. And this is equal to 5 times 18 minus 36 plus, and then we're just going to move the power of 2 in front. So which means this is 4 times ln of 3. And then we have minus 9 times ln of 3. Now combining the like terms inside the bracket is going to give us negative 18 minus 5 times ln of 3. And finally, we can now distribute the 5, which means we get a final answer of negative 90 minus 25 ln of 3, which is exactly what we were trying to show. And now let's do a quick recap of what we covered in this video. We learned that the sigma notation is just a mathematical shorthand command directing you to sum up a sequence of terms generated by a single explicit formula template. And because the terms include both the lower limit and the upper limit, in order to find the total number of terms, we always need to take the upper limit, subtract the lower limit, and then add 1. And lastly, don't waste time expanding out the entire series. Expand just the first 2 or 3 terms so that you can classify the underlying progression, and then transition directly to your sequence and series shortcuts. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other sequences and series topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.